Hi everyone, welcome to my presentation today. A paper entitled Online 3D Deformable Object Classification for Mobile Cobot Manipulation. My name is Ken. Our team includes me, Tuong, and Dr. Huber. We are from Learning and Adaptive Robotics Lab of the University of Texas at Arlington. So, as we know, assistive mobile cobots can be used to grasp or manipulate a lot of everyday objects for service tasks, especially for indoor robots. So, for example, we will have a lot of robots to assist our kids, like to grab the teddy bear or their dolls. Secondly, we will have a lot of robot in the kitchen that will grab your snack. So for example, right here we have the Google robots from their labs. Or thirdly, we have a robot to grab a can, right? Like in this image is our case. So, but we all know that some objects are easily to be deformed due to the inefficient grasping force of robots. For example, human factors. For example, we have a can right here, and if I squeeze it and I grabs it, the can will become deformable. So this actually makes a challenge for the robots to classify what are those objects in the deformed shape uh, to grasp it efficiently in later manipulation. So in brief, here we solve the problem called misclassification problem. So what are our contributions? So our contributions is firstly generation pipeline for deformed objects from 3D scans. So as we can see, so that is the first thing we should have in our pipeline. Secondly, we develop a lightweight machine learning model to classify objects with deformation artifacts. So which is the second step in our pipeline is training and testing the lightweight model. So lastly, we have to guarantee the online inference on such system, and so the third step in our pipeline is deploy the machine learning model trained on the auto-generated dataset on the real robot system. So first thing we have to do is scan the deformable objects that we collected in the real world. So as we can see on the right side is our 3D scanner from MechBot. I use it to scan the objects that are on the left of the figure. So our objects include a lot of cans, cups, and foam bones, which are deformable objects. So for the first step, we scan the object. As you can see, we start scanning the soda can. So next step is we gonna start sampling the scan objects just for the performance while generate the deformed objects in later steps. So secondly, we will identify the graspable region on the object. So for example, we have the can here, and the graspable region is colored in red, as you can see. So that is the region that the robot usually grabs the can. Thirdly, we will sampling the handle points. So we sample the handle points in a uniform manner, so which is largely distributed across the graspable region. Next, we take the sampling points for multiple deformation, as the robot has 2 grippers or 3 grippers, depends on your robots, but it of course it has at least 2 grippers, and slightly slicing the object for the position of the opposite hand point. So for example, we have one handle point on this side and we have another handle point on the opposite side of the object. So next we will define the inward orientation and the deformation intensity for our pipeline. So for example, how hard you want the deformation will be, and the orientation, so which means the inward orientation when you grasping something or your robot grasping something. And finally, we will generate the deform mesh. So as we see at the final of the pipeline, we will have the deform mesh of the scanning object, which is the soda can. So we will talk briefly about the as rigid as possible deformation with smooth regularization, which is the main technique in our deformation pipeline. So as normal, we will denote the deform mesh M as the set of edges, which is E in capital, V in capital stand for the vertices, and F in capital is the faces of the mesh M. So likewise, we will denote the deform mesh as M prime with E prime, V prime, and F prime, which are the geometry entities in the deformation manner. So we would like something like M prime from M, right? So without lots of generality, we arrange the vertex in the deform mesh M prime as follow. The first M vertices are constrained vertices, so which are invariant to the vertex VI in the original mesh M, and the rest vertices are the transformation of the original ones. So it represents as the TI, which is the transformation of the original vertex from the original mesh. So this is the main formula in our generation pipeline with smooth regularization. So as we can see on the right is the drawing of the mesh surface. So I will explain the formula right here. So first we want to optimize the loss based on the set of the transformed vertices in the deform mesh. So it includes two components. The first one is the differential term, which portraying the curvature loss along the surface of the mesh in deform and the original one. And the second term is the smooth regularization term, which is can be tuned for the smoothness along the curve, along the surface. We don't want it to be so harsh. We want to be as smooth as possible. So how does the formula in the generation affect on the data set, on the raw scan look like? So here is the subset of our data set. So our data set includes a lot of deformable objects. Like you can see, there are a lot of balls and deformed, cups and cans in deform. And of course, I view this using Open3D library. So the main question here will be how well the data set distribute in terms of deformation loss on the generated data set. So this is how it looks like. So the deformation loss in this particular scenario will be computed at the weighted loss of the chamfer distance, which illustrate the similarity between the deformed mesh and the original ones. The mesh edge loss, so when the edge is deformed, how different it will be compared to the original one. The mesh normal loss, so which means the two surface, if it's original look like this, or after bending it will be look like this. So we compute that loss. And the Laplacian smoothing loss, so how well the surface curvature compared to the original one. So intensity in this figure, you may ask, so it presents the inward displacement of handle points. So for example, 4 pixel, 6 pixel, 8 pixel, 10 pixel or so. So from this figure, we can see that it will distributed across the domain. So next we create a network for deformable object classification. First, it takes in the sampling points with deformation artifact as input, and it will pass the data through the spatial transformer, subsequent by 2 convolutional layers and 1 fully connected layer, as we can see in the figure down there. The reason we use spatial transformer here is to find the representation of the objects that is invariant to the permutation, rotation, translation, which is induced by the nature of point cloud. So when you have it in an order manner. And lastly, our network will return the probability among the classes at the output layer. So in this particular scenario, it will decide what the objects will be. Is it a can, a cup, or a ball, and in which size? So we will talk briefly about the training performance of the design network. So the network are trained on the RTX 4090 GPU, which batch size of 256 in 58 pulses, and the training time takes about 10 minutes only, so which is very fast. And I tried it with different N and F combination. So N represent the sampling point, and F as the feature number of features in the network. And this is how it looks like, and they are achieved a reasonable accuracy of 90%, especially for the model that we use 80 features. So how about the testing performance of our design network? So this is the confusion matrix I constructed when reclassifying on the dataset. So the dataset includes 70% of training dataset and 30% of the testing dataset. And as we can see in the figure right here, the model using 80 features with 62 samples is the best one. It achieves almost the accuracy of 99%, except it misclassified the small ball and the tiny ball right here, which make it lower a little bit. So our conclusion right here is more features the network learn, the better the accuracy achieves. How about the training parameters and model size for our models? So as we can see here, most of the model has the size less than 100 kilobytes and has about 5,500 trainable parameters as the best model we achieved in the last step. So our conclusion right here is it's suitable for on-robot deployment. So first, before coming to the demo, I would like to introduce the GitHub repo. So I also upload all the code for public use. You can refer to it if it may use in your future research. And here is our demo. So first thing is communicate between the computers, and then rotate its hands to take the deformed object in multiple view. And after taking this view, it register all the point clouds as in one, And once it had the registered point cloud, the point cloud will pass into the network to classify what object it is holding. So for example, in this scenario, the object is classified correctly as the medium can. And I think that's all for my presentation. Thank you for listening.